right. Good morning, everyone. 大家早上好，请问可以听得见我讲话吗？ All right. Okay, so 整个 workshop 我会用英文去present 啦。First thing. Okay, good morning, everyone. So welcome to the advanced workshop. Right, so I am Dr. Sanjay Sun. So in here, I'm going to present to you the advanced levels of the programming. So it would be more on the data structures. If you have actually joined the fundamental level, so you come into the advanced level where it is on the data structure. Last week, it has actually discussed about pointer, linked list, queue stack, and all that. So that would be the fundamental. Okay, so for this week, so for this workshop, what that we're going to present is more on the advanced level that we'll go into the non-linear data structures where we're going to talk about recursion, tree, and also graph. So let me start my video so that it will not affect the connection. Okay. All right, so now we're going to start with the content. So these are the things that we're going to present over here. First is the introduction to recursions, then tree. So for tree, we have binary tree, binary search tree, and graph. We're going to go into the depth first search, breadth first search, shortest path, minimum spanning tree, and also some of the examples. For recursion is actually the functions that call themselves. So can you only solve a base case that it will divide problems up to what it can solve, what it cannot solve. So a function normally that is going to launch a new copy of itself to solve what it cannot solve. So eventually the base case gets solved, get plugged in, works its way up and solve the whole problem. So probably thinking that I'm just reading the whole thing, right? But don't worry, that I'm going to show you the examples that how the recursions that it's actually working. So for the tree and also for the contents that we have mentioned just now, they are actually using the recursions. It can use either recursions or iterations to solve it. So to solve the problems that trees and also graph, first thing you need to know about is recursions. Examples over here, okay? Recursions also occur when a method invokes itself to do part of its work. So from the functions that shows over here, first thing is that we have public void T1. So T1 is the functions. And we have another one which is actually in the T2. So what happened is that when you see in T1, after the executions of T1, it will go to T2. But when it comes to T2, it goes to T1. So repeat again, go back to T1 and go back to T2, go back to T1. So this one, it will happen again and again. And you need to have a base case because it's kind of like it's trying to iterate again and again. So it might go until infinity because you have to stop it at a certain limit. So that's why you need to have a base case to stop the recursions. So recursions, it has two parts. One is a recursive case where every recursive call must either solve part of the problems or reduce the size of problems. Then we have a base case that non-recursive part to actually terminate. So we're going to use this case study, which is a factorial, that to explain on how recursion works. So if you're using the iterative methods, you're going to use the loop to calculate the factorials. And you can also use the recursive methods. When we look at the iterative methods, that when one, okay, it would be 1 if the n is equals to 0. So this one, it will be the base case, because when you start to iterate it at one time, that you're going to go and the n will reach to be 0. Then you assign it to be 1. But when n is greater than 0, then what you need to do is you have to n multiply with n minus with 1, multiply with n minus with 2, and so on until 3 multiplies 2 and multiply with 1. But when we look at the recursive methods, that we also have a base case that when n is equals to 0, then you're going to get 1. However, when n is greater than 0, then it would be n multiplied with factorial n minus with 1. When we look at this factorial n minus with 1, it is actually similar to this fact 0 here. So now since this has become 0, so it means that 0 plus with 0. Okay, so it goes to 1 plus with 0. Why? Because when I return sum 1 minus 1, it is 1 plus with 0. So it means that this whole thing with it is actually sum 1, that you get the values of 1. Revert back. Okay, revert back. Don't forget that you have to revert back where you get this sum 1, it is actually 1. So revert back here, you get the values of 1. You have to 2 plus with 1. You get 3. So you get 3. Go back. Okay, you have to go revert back. That as because you're actually returning the values where sum 3 minus 1, which is sum 2, you get the values of 3. Then eventually 3 plus with 3, you get the values of 6. So here you're going to return the value. Eventually it's going to be 6 steps. You see out the results, you get the values of 6 over here. Okay, so it is actually going into the function deeper and deeper again until you reach the base case, where in this case here, the base case is 0. So when you reach a 0, that it cannot proceed anymore, right? So it will reverse back, okay, do whatever that is needs to reverse back and gets the reach until the first stage. Then it will give you the values that you want. So this is the sum. Now, if we look at the factorial case, so the examples I'm going to show here, it would be either in the iterative way or in the recursive way. The values that I'm going to give, okay, just a very simple and small value, that we're going to have this 3 factorial. So for 3 factorial, you know that the values that we get is actually 6, right? Because 3 factorial equals to 3, okay, multiply with 2, you multiply with 1, you get 6. Okay, in here, we call as factorials of value by recursive factorials. We call this function. So this is a function where we're going to pass in, okay, value, it would be equals to 3. Here, if the value is equals to 1, return 1. So this one would be the base case. Okay, so we see out the values we get is actually 3. Okay, in the first round, the values is actually 3. Then we go in, that will trigger the recursive factorials of 3, because it's from 42, it's going to return the value multiplied with recursive factorial value minus 1. So similar to the sum examples that shows just now, where it will call the function again. Go into deeper where this one, recursive factorial 3, it will be 3 multiplied with recursive factorial 3 minus with 1. But what is the recursive factorial 3 minus with 1? It is actually recursive factorial 2. What is the answer for recursive factorial 2? Don't know yet. Go back to the function again. Okay, it will be recursive factorial 2 to 2 multiplied with recursive factorial 2 minus with 1. When it reached this recursive factorial 1, so it means that it's actually 1, right? The value. What happened? It passed in the values of 1. When it's actually passing the values of 1 means that you have to return 1. So that's why you can proceed with 2 multiplied with 1. Okay, from here. That you get the recursive factorial 1 is actually 1. So 2 multiplied with 1, you get 2. So now we know that, okay, recursive factorial 2 is actually 2. Reverts back. Okay, we have to go back to the previous, where when 3 multiply recursive factorial 2 over here. So you get 3 multiplied with 2, you get the values as 6. So eventually, you will get the value to be 6 over here. What if we solve it in the iterative methods? Okay, we create another function, which is iterative factorial. Same thing, we pass in the value. The value here, this one would be equals to 3. Comes in, do some initializations where factorial value is actually equals to 1. Okay, do it in iteratively. First iterations, I is actually equals to 3 because the I that we initialize, we put in to be equals to 3. Check on the conditions that 3 greater or equals to 1. Yes, this one is actually true. So it means that we're going to go into the functions. Factorial value, okay, is equals to 1 multiplied with 3 because the factorial value initially that we have is 1 multiplied with the I, which is actually 3. So we get 3. But then, of course, you have to update the values of I. In the second iterations, your I will be equals to 2. Then check on the conditions that 2 is greater or equals to 1. This is true. Calculate the factorial value again, where previous the factorial values we get is 3. So with 3 multiplied with 2, you get 6. Again and again for the for loops until the conditions is actually false when your I is equals to 0. So how do you reach that the I equals 0 is based on this decrement value here, the decrements of the I over here, where eventually become false, then you'll get the final outputs to be 6. So you return the factorial value. It is actually 6. Both methods, it's the same. I mean, any methods, as long as you can get the answer, it is okay. Okay, either you use the recursive methods or you use the iterative methods. It's the same thing. Okay, the idea is basically the same. Okay, so we're done with the factorial. So now what we're going to see is we can actually use it to solve another problem. Okay, this is a factorial, which is Fibonacci. So in this, okay, your mind will have to be very clear about how this is actually working, because it's going to keep repeating, going deeper and deeper until that's probably some extent that you're going to lose. But you just have to think, okay, to be clear that how does the recursive actually works. Okay, so now if you go into the Fibonacci examples, where it's asking that how many numbers that you want for the Fibonacci series. Okay, so let's say if I key in 4, okay, you give me the result of 3. Okay, so how do we get the 3. So is it really 3? Okay, because if you look at the samples over here, 0, 1, 2, 3, 4. Okay, it indeed that you're going to give you the 3, right? You get this 3. You start from 0, 1, 2, 3, 4. Okay, so that's why you give you the values of 3. But how do we actually get the 3? So when you see out, you call the function, which is fit, like means that's a Fibonacci, and you pass in the value. So we're passing the values num here are key in as 4. So pass in to be num is equals to 4. Same again that we need to have a base case where if the number is equal to 0 or is equal to 1, that will return the num. Else, it will return the values of Fibonacci, okay, num minus 1 plus with num minus 2. So let's see the flow. Okay, in the first round of the recursive is Fibonacci 4 minus with 1, then plus with Fibonacci 4 minus with 2, right? So when it's actually calling 4 minus with 1, it will trigger another. It will go back and trigger the functions over here, recursive, where 4 minus 1, basically it is actually 3 minus 1 plus with 3 minus 2. But when it calls this 3 minus 1, in fact, it is actually repeating to the functions where it will be 2 minus 1 and 2 minus 2. So when it comes to 2 minus 1, it will becomes Fibonacci 1. Okay, when it comes to the functions, it says that n equals to 0 and n equals to 1. When the n equals to 1 means that it will give you the values of 1, right? So here it would be 1. But we still have is not the n yet because we still have Fibonacci 2 minus with 2. That it is actually 0 because the values that pass in, the num will be equal to 0 means that it is 0. So it will be this Fibonacci 3 minus with 1, we get 1 plus 0 that you get 1. Okay, so we only solve this 1, but we still have 3 minus 2. So what is 3 minus 2? It is 3 minus 2 with, it is Fibonacci 1. You get the value as 1 over here. So which means that in this, okay, it is actually 1 plus 1 that you get the sum, okay, Fibonacci. 4 minus 1 you get as 2. So it means that you solve this first part, but you have the second part, which is Fibonacci 4 minus 2, where go into the function again, repeat itself, where Fibonacci 2 minus 1 plus with Fibonacci 2 minus 2. So you get all the values that eventually 2 minus 1, you get 1, okay, 2 minus 2, you get 0. So which means that Fibonacci 4 minus 1, it is 1 plus with 0, you get 1. So 4 minus 1, you get 2. 4 minus 2, you get 1. Means that 2 plus with 1, you get 3. Eventually, when it comes to the end, okay, after you finish down the recursive and repeat everything back, you get the result output to be as 3 if the series is actually 4. But then, of course, if your num, the value is larger, let's say 100 or even larger, then you have to keep repeating all these for many times. So this one, it would be the run it in the recursive way where it calls the functions back itself. Okay, so this one is the Fibonacci example. Okay, so then now we go to another example that I'm going to show you is the Hanoi Tower problems that you can actually solve it in recursive way. But for this one, it probably is actually quite confusing. Okay. I hope all of you know that what is the Hanoi Tower, right? Let me show you what is the Hanoi Tower. Okay, so this is a Hanoi Tower where, let's say, okay, the reference that we get it, okay, from the Geeks for Geeks. So this is a Hanoi Tower problems where it has 3Ds and you have 3 poles over here that you're trying to move all this to the C. So first, this here you move to C, and then the second this, which is white color, you move to the second pole. And then you move back the first this to the second pole, then you move the green color, the largest one, to the third poles. Okay, until you've done all this, you get this one as the N. So which means that you have successfully moved it from A to C. But of course, the rules, there's a certain rules that you need to follow is the this that is actually under, it cannot be larger than the one that is on top. So these are the rules that we need to follow. But how are we going to solve this? Using the recursive methods. Okay, so this is the outputs that we get. Okay, so now first thing is n equals to 3, which is number of this. So let's say we have number of this is 3, that we follow these examples over here. Okay, then immediately, second one, we call the Tower of Hanoi, which is the function that we're going to pass in n, the numbers of rods. 3, okay, A, C, and B. A, C, and B that we come in over here. So this is the functions that we're going to start the recursive. If n equals to 0, then we just return to where it comes from. Then we go start to call the Tower of Hanoi, n minus 1 from, okay, auxiliary rods and 2 rods, which is from where to where, and which one is the supporting auxiliary rod, which means that which one that you're going to do the support. So in this case, all right, so first thing when it actually comes in is 3, A, C, and B, right? When it passing through the functions. Means that from is A, auxiliary is B, and 2 is C. Okay, when it first pass in now, which is actually from here. Then it will call the function, which is Tower of Hanoi, inside the function itself. When it calls and you need to pass in with 2, okay, it would be A, B, and C, because from, okay, you go into the from, which is A. 2, you go into the 2 over here, okay, by name, it is actually B, right? Okay, 2 is actually C, sorry. But you got to put in, okay, you have to fix. Because in the second place here is actually auxiliary rods, where it is actually B. Because you remember that in the first, when you pass in this ACB, that aux is actually B, so we have to arrange it that A, B, and for the 2 rods, it is C. So we go in that 2, A, B, and C over here. Call the functions, come up. Okay, so when it comes in, is not n equals to 0 yet, right? Because we pass in as 2. So 2, when it comes in, is 2, A, B, C, where from is A, okay, auxiliary, it is actually the C, and 2 is the B. Not n yet means that we have to call this Tower of Hanoi, this function again, where it is 1 ACB. Okay, so from is A, ox is sorry, is C, and 2 is B. So we come down, go in again. That's where N equals 2. Then it becomes that 1, okay, ACB. Then you repeat again until your N is 0. Okay, it goes back N equals to 0. So when it actually ends to 0, what happens? It starts to revert back that because it's going to returns, right? When it starts to returns, what happens? It comes over here, that is going to come down over here. Where C out move this N from rods, okay, to which rod. So when we come down over here, okay, we get it from here, where it is this one. It is actually from, okay, you can see here, from to this rod, which is rod of C. So you move this one from A to C. Okay, then we have successfully moved from this one, from rod A to C, right? So what happens? We have to go back. Okay, we have to go back to the 2 parts that we have actually solved this. We have to go back to the 2 parts. And same thing also. Okay, we're going to see out that you're going to move these 2 from A to B and move back again. That you're going to get moved this one from C to B and so on. Okay, until repeat again and again. Okay, until it is reaching the end of the recursions. So that's why you can get this output over here. Okay, I'm not going to explain, go through to you one by one, but you can actually, if you have time, okay, you can go back and trace it one by one slowly by yourself. Okay, be careful that it's actually quite confusing. Is here that how the idea is going to work is that, let's say this is a tower of Hanoi. Okay, not true for this, but it's actually a 3D where you can actually, how does it actually move? And it is actually solved through this recursions, tower of Hanoi, that you pass in all the values. One thing that you need to know is the logic. Okay, it has to be very clear. Okay, due to time constraints, so let us move to the next part. Okay, this one is the recursions. So this recursions, we're going to bring it to the tree. Okay, let us continue. We're going to go to the tree that we're going to implement tree. So when you talk about data structures, you can actually arrange your data in the tree forms. Let's say the family tree. In the tree, what we have roots, we have leaves, and also we have branches. The one that are at the top here is considered as a root. So from the root, we expand. Okay, we expand E and L. Okay, E will be the left side of the H, and L will be the right side of the H. Start to expand again. Okay, just like a family tree where it's going to expand, right? So E, expand, maybe get married, okay, and expand that you get B and F. So L also expand J, M until the end. So the one that we have, you can see that each of these nodes here, leaves here, they have connections with each other. Okay, so that we know that, okay, H, it has left son and you have a right son. Same, right? You have first son, okay, maybe the second one is daughter, or same over here, that you have branches to show you where does it actually expand to. Okay. So it's like a view of a tree in the upside down. Here is the root. then it starts to expand. Then it has leaves, and then the branches that shows that, okay, which leaves is belong to which branch. But then of course, a tree, if it is too big, then you wouldn't know that which leaf is which branches, right? But if you want to trace, it is actually possible. So let's say you want to trace back who is your ancestor. So probably you can actually trace back, okay, maybe you are the son of once emperor or something like that. So that is how the tree works. So why do you study the trees? Is finding that it would be easier when we look at in the hierarchical way. So let's say the structure, it has the hierarchical relationships between the nodes. Then it is actually easier to solve if you put it in the tree. If let's say we don't have a family tree, do you know that who is your ancestor? Do you know who is your great-grandfather or who is your great-great-grandfather? Well, if you have a tree, then it would be easier. Then you can go, okay, follow this. Okay, I'm from this branch. Okay, and then, you know, okay, this is my father. And then this is my auntie, who is my uncle. Okay, you know all these things. Why? Because all of these, they are in a hierarchical relationships that you can trace back. So the conclusion is link data together in a hierarchical manner that help to solve problems related to hierarchy. Terminologies. Each tree will have a unique node, which is called roots, which is the top node, right? Because you need to have a root, then only you can start to expand. Tree has recursive parent-child relationship between the nodes. For example, here, E is a son of H, where H is actually the parent. Like, let's say F is the son of E, but which son? Right. Okay, is the right son of E, and E is the parents for B and also F. So these are the relationships for the tree. Okay, then we go to the tree that we have subtree. Okay, subtree is a collection of nodes and its descendants. So let's say A, B, C, D here is actually a subtree of B because it's actually expand from the B, with B being the roots of this subtree. Okay, so let's say here, okay, maybe this is your great-grandfather, then your great-grandfather, you have two sons, which is E and also L. So E would be your grandfather. So when it comes to the B, okay, maybe it's your, okay, we assume that it's your father, but your father, you have two kids, and then the kids is actually start to expand. So your father is the root for the subtree, I mean, for your family over here. But when it goes, I mean, connect back up, that is actually from your grandfather. So this is how the subtree is actually looks like. Of course, it can have more than subtree, more than one subtree. It depends on how you're going to divide your subtree. Okay, so in here, so let's say we divide this part. Okay, this is actually the E and this is the L, where this is subparts. Why? Because if you, let's say, want to know the numbers of nodes of TH, so what can we do is we just can plus this. Okay, we calculate the nodes in this part, which is TE, and we calculate the parts in TL. That how many nodes do we have? Then we plus it all together. Then we will know that numbers of nodes in the tree itself. Okay, but of course, if the tree is actually empty, then we'll say it as 0. Otherwise, it will be 1 plus with the numbers of nodes in the part E. Okay, this side, and then we plus with the side of L over here. So can generalize that the subtree concept a tree with more than 2 sons for each parent. So a tree is either empty or it consists of a n0, okay, nodes such that n1, n2, and nk are its children. You can see that one root, it can have a lot of children. Then from here, we actually start to expand. Then n1, n2, nk becomes the roots of a subtree. So this n1 is actually the subtree where it is t1 until the tk. So each of these n1, n2, n3, and nk here, it is actually the root of the subtree itself. So how do you calculate? You calculate by 1 plus with t1 plus t2 until tk. So same, okay, we have nodes and edges. So this is the nodes where just now, okay, it is the leaves, but here is the roots. Okay, this is the leaf and edge. This is the branches, right? So we have these sibling nodes that have the same parents. Let's say B and F. Okay, the parents is E. So we can call B and F as a siblings because they are from the same father, which is E. J and M, they are siblings too, okay, because it's from the father L. F and J, we cannot say as a siblings because they are not from the same parents node. So we have leaf nodes where, okay, nodes with no child, axonal nodes with it is a leaf node, and internodes is the nodes with sons and those other than the leaf nodes. So this, which means that this one, we call it as axonal node. And this one, let's say B, we call it as an internal node. Okay, now we look at, after we talk about all the trees, things that you have son, I mean, it has parents and how do you calculate the nodes and all that, we need to know that what is a binary tree. Okay, binary tree is a tree that molds that you have 2 sons for each father. So which means that I either have 0 or you have 1 or you have 2 children. This is the conditions for the binary tree. Let's say H over here. It fulfills as a binary tree, right? Because it has only at most 2 sons. Same for the C here. Okay, it has 1 children. A don't have children. This whole thing, it is a binary tree. While it can be empty, or it consists of nodes called together with 2 binary trees like left subtree and right subtree. This is how a binary tree looks like. But if let's say H, okay, it has more than 1 son, then we don't call it as a binary tree anymore. Okay, either of the subtree can be empty, and a binary tree may not be balanced. As an example shown over here, you can see that B, okay, it has 2, E and ABC here, but then, you know, it's slanted to the right-hand side that it keeps expanding over here. It can happen, okay, no ordering is required on binary tree, can store information at any nodes in any arbitrary manner, like the tree on the right. But of course, that when you're actually arranging your data is in the binary form, you have to know, okay, what is the patterns of the data so that you know how you can actually arrange in the binary tree, right? It has to have some patterns. You cannot just simply, you know, okay, this one, okay, I like to, okay, put it into the right side. Then the next one, okay, also the next side. No, it has its own patterns. But how do you come up with the patterns? It actually depends on the data or how you want to arrange your data in the tree itself. When we have trees, we want to travel to the tree. Probably thinking, why I want to put data in the tree? Because you want to travel to the tree to visit to the every node in a systematic manner. Okay, so later I'll show the examples that why do you want to travel to the tree. Okay, ideally, that each tree node should be visited once, but in reality, okay, the tree traversal function here will visit each node exactly 3 times. So later we'll show you that how you can actually travel to the tree, that how many times that you can actually travel. So the foundations of any tree operations, that most of the tree is tree travels and simple operations. So let's say you're trying to count the number of tree nodes. Then one needs 3 travels and passing a counter to get increment by 1 at each node. So what does it mean by, let's say you want to travel, you want to calculate that how many nodes do you have in this tree? So what you do, you go from roots, okay, you start to travel all around the tree, okay, to start to calculate that how many nodes that you have. Okay, but what is the purpose of calculate how many nodes that you have? Well, it actually depends. It must have a purpose, right? That you want to calculate the numbers of the tree nodes. How to do the binary tree traversal? Okay, normally in the binary tree traversals, what happens is for a tree, you have branches that you have left and right that show you just now. Normally what they will do is you go to the left side first, okay, travel to the left side. Then after you're done with the left side, okay, because sometimes when you reach that there is no more extensions, no more branches, then you go to the right-hand side. So all these done in the recursive modes. Okay, visit the left sun first, okay, since the purpose is to travel. And then after done with the left sun, you go to the right sun. So if you ask me, why don't we just go to the right sun and then go to the left sun? Would it be not fair? But then, okay, this is just a tree that the patterns is go to the left sun, then go to the right sun. But then, of course, if let's say you want to think about that, I want to visit the right sun first, then only go to the left sun. Yes, you can do so, but just make sure that everything is working properly. Okay, but when after you visit all this, right, at the end you have nothing to visit, then you have to click on the empty tree. Okay, you can see here any tree operations without this pattern embedded will be likely not working. So if you're asking me that you go to the right and then go to the left, is it working? Well, you can try it out yourself and see whether it's working or not. Okay, so tree traversals guarantee that each node will be visited in a fixed order as shown below according to the arrow. So let's say we start with a D. Okay, we go to the B, 1, 2, then we go to the A. When we reach A, it will follow these algorithms. A here, you have to go to the left and right. So even though you know that for A is actually the last nodes, that it doesn't have a left and right, but you still have to go to the left and also the right also. Then only, okay, you go back to the B. And then same for the C is B, you come down. Even though you don't have the left and right, you still go in and go to the left and the right and then go up. Then you backtrack, okay, back to the D. Because you have visited the left side, the left side here is the 1, and then now we are going to the right side. So come down. Okay, same pattern. That's what happened. Okay, go to the left here, and then go up until the end. So the traversal patterns, we can summarize it that is in the counterclockwise manner, okay, as shown over here. So in total, 15 copies of TT has been created with each processing of 1 notes. So to highlight that the TT functions, the traversal functions are recursive because you can actually call the same functions which is own body. Okay, this is just the concept. So this TT here, you can see when it tries to go to the left, it go back. Okay, it pass in the notes. So this notes that, let's say it is a left notes, it go back. Then it will returns when, let's say it doesn't have any notes. So you can see here like A, you don't have any notes, then it come down. After it's done with the left, then it goes to the right. Like A here, if don't have a right light, then it goes back. Then it will return nothing. So the pattern is go to the left, then go to the right. For the nature of the TT, it's always in the depth first. Depth first means that it will always go down to the deepest level until it cannot find anything. Then it will reverse back to until it can find something. Right? So it is actually in the depth first nature for the tree traversal. So for the processing order, okay, it has its own processing order. But when you're visiting the nodes, okay, when you're visiting the nodes for the tree here, you can do it as a pre-order, in-order, or post-order. For pre-order is that you process the nodes in the first visit. In-order is you process the nodes in the second visit. Post-order is you process the nodes in the last visit. Because if you remember that I've mentioned, okay, in realities that the nodes, it has 3 times of visits at most. You have 3 times. So post order will be the last visit, where it is the 3rd time of visiting. So how do we actually know that first visit, second visit, last visit? Later, I'm going to show you the examples. Why do you actually bother on the processing order? Okay, does it actually matter that how you travel to the tree? Well, it is actually matters. Let me go to this one. Okay, it actually matters that how you're going to process the tree. Okay, but it might not matter that whether you visit your friend or taking the lunch first, but it does matter when you're doing cooking, running a chemical experiment, dressing up as a Superman, right? So like when you're dressing up as a Superman, you wear the pants first or the socks first. Of course, you need to wear the pants first, then you wear not the socks, it's a shoe. Because you cannot wear the shoes first, then only you wear the pants, right, for the Superman. So the order does matter in this case. Like when you do cooking, you want to cook Maggi mee. Do you cook the noodle first or you cook the soup first? But of course, it actually depends. Some people, they cook the noodle first, then they cook the soup. But most of the time, we cook the soup first. We let the water boil first, then only we put the noodle inside, right? So the order does matter, depends on the task. All right, so like we can have the tree to be top down. Okay, if you want to process the tree from up to down, then it would be pre-order. If it's bottom up, then it would be post-order. Okay, so for example, here, pre-order. For pre-order, if you remember that the nodes visited first time. So let's say here we visit the D. This is the first time I encounter D, right? So I want to print out the notes, the name of the notes that the first visit. So I print out the D here. Then I travel left or right, left first. because the pattern is always go to the left, then only it goes to the right side. So you go to the B, print out the B, because B is the first time that we encounter. Then we go to the A. Okay, for A here, still, even though you know you don't have any notes anymore, but you still go to the left, then you go to the right. Then we do backtrack, go back to the B, because since B already printed, so what happened? We don't print it anymore, because this is the second time that you visit. So B, we still have the C, which is left side to visit. When it comes to the C here, this is the first time that encounter, so we print the C. Then C also the same, that you have to go to left and right. So after done, okay, you go back to B. Then we do backtrack. We go to D here. Done with the left side. Now we go to the right side. F. First time encounter, so you print it out. Then you go to the E. Also the first time that you encounter, you print out the E. After that, you do the backtrack. You go to the G. And G will be the last one, right? Because you have visited all the nodes here. So this is a pre-order where you print a notes when you first time visit. Then what about in order is the second time. Okay. When you go to the D here, this is the first time. So we're not going to print out the D. You go to the B, also the first time that we encounter. Then we go to the A. Okay, when it comes to the A here, remember that even though A, you don't have the notes, you still go to the left and go to the right, right? So when it goes to the 4 here, I mean that second times that it encounters, so we print out the A here. Then we go to the 5, and A, you have to backtrack to B. When you backtrack to the B means that it's the second time that it encounters the node B, so it prints out. Then it goes to C here. It prints out when it returns from the left. Then backtrack to B, backtrack to D. When backtrack to D over here, it is the second time, so we print out the D. Is it going to print out the F? No, because this is just the first time. So it goes to the E here. And you can see that when it goes return from the left, it prints out. Then go to the F, only it prints out the F. Then G, it print out the G. Then it backtracks to the D. So the order, okay, you can see that the order of the notes in pre-order and in order is different, because depends on the notes that visited. Is it the first time, second time? And if we go to the post order, would be the third time. So we'll see that whether the order to print out for the post order, is it the same? You can see that it's not the same. D, when it comes down, this is the first time. Okay, when it comes over here, it will only, A will only print out when it's go to the left and the right. But when we backtrack to B, is it going to print out? No. Why? Because only the second time. Then it goes to the C here, that you have left and right. Already the third time, then it print out. When C backtrack to B, then only it will be the third time, and only it will print out. So same for the right-hand side here, okay, and then you print out. So you can see that over here, the last one is D. Why? Because when it first come in, then you have to go to the left, and then when it comes back from the left, it's only a second time. Then it goes to the right side. After it comes back on the right side, and only it's actually visited for the third time, then only it will print out. So this is the difference, okay, between pre-order, in order, and also the post order. But how are we going to look at this? Okay, so we just straight away go to the pre-order. Okay, for example, that is how your tree looks like. The H, you have E, L, B, F, J, N, and all this. So this is in the pre-order where it's going to print out when it's actually in the first time. We go H, okay, E, B, and A first, right? You can see H, E, B, A. Then it goes to C, D, E, F, no, E, F, F, G. Okay, then L, J, I, and K, M. When we do the codes here, is first thing we will create the notes, and we will put these notes into the structure. Last week, probably learned about the structures of the class. Okay, so if you look at this notes, okay, with a star of roots. So this one is the pointer that is actually creating the new nodes to store, to construct the tree. Remember, like the linked list, that you need the pointer. So if we go to the node here, we see what is actually a node is about. So it's something like this, where it is the structure of the nodes. And we try to store data to be a character instead of number. So it is a character. So our type here is a character. And we have left nodes and also the right nodes. In the nodes itself, we have the constructor. That one is actually being called. So we'll store the data. And we have the left and the right to be noun first. So when H come in, okay, H would be the data, which means that it's actually the roots or the source of the tree. So when you start to build, you can see here that roots left is E. Okay, go to the left, that is actually E, and L here, which is the right, that's L. Start to expand, roots left, 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 left. So this one is B, and right, left, right, then left, right, then which is E. So of course, until the last one, which is left, left, right, right, left, left, right, right. So it's actually D. So follow. Depends on how large your tree is. So this one is considered a small tree that you're putting it in this form. Okay, next is that we go to the order of the roots. Call the functions of order for the roots. So this is the functions where it is order for the roots, where we're going to travel in the pre-order. First thing, since you're going to print out the first times of visits, right? So we just see out the root data, which is actually the H. And then you travel to the left subtree. So what you do is you pass in the roots or the left subtree and call the functions of order. So what are the functions of order? Repeat is a recursive. So go back, come down over here. That's you're going to print out. So let's say we go to travel to the E, right? So which means that in the second round, the root data would be the E. Okay. Then again, it goes to the left, which is the B. You kind of go to the right because every time that it's actually repeating, it will always go to the left. So you go to the B and then goes to the A. When you're actually reaching the A, you have to check, right, where is it the empty or not? Because after the A, there's nothing here. So that's why it's actually returned. After it's returned from the left, it will go to the right. But for right side, also nothing. So it will return also same thing. But when after it's returned, what happened? Backtrack to the B, because remember that it's a recursive, means that it's going to reverse back. And then if it comes down to the C and print this, and then if it goes to D and print out, after it comes to D, go to the left and right, nothing happens because eventually it's going to be a null pointer. So backtrack, okay, and then same thing, okay, again and again until the end, where you get the end. So this is actually the pre-order. And how you can actually arrange, it actually depends on the whether it's a pre-order. Now, if you look at the in order. So in order is the second time, okay? You print out when during the second visits, right? So is it going to be same pattern as the, is it going to be same as the pre-order? Okay, the way that we actually construct the tree is actually the same. So now if we go to the order, so if we go to the order here, it's the second times when you print out only when you encounter on the second times, right? So H, first time, no. Okay, go to the E, go to the B, go to the A. Yes, we'll print out the A first, then print out the B. Because when it backtracks means that it's already the second time. So you go to the C, okay, then it goes to D, then print D, okay, then yes, let's print C, okay, something like that. But when we look at the functions itself, is in order. In the pre-order, you print the data first, right? But in the in order, you print out after it's actually receiving the left side. Then what about the post order, which is the third time that visits? Okay, is it that you just change the order of the travels? You just change the order of the functions here? Well, the answer is yes. You just change the order of the statement. So let's see, we go. Okay, forgive me if I'm going for too fast. The way you construct the tree is the same, but you can see here, when it is a post order, that you print out last when you encounter the notes. After you go to the left and you go to the right, then at the third times, you go to print out. Only you will print out. So if we try to compare that first in the pre-order, you print out first, second time, okay, print out in the second, then third order, after you go to the left to the right, then only you do the C out. So this is the difference between the pre-order, okay, and in order and for the post order. So it depends on how you're going to arrange your quotes when you try to travel to the tree. Okay, so this is the tree traversals. All right. If we go to the next one, is the binary search tree. So it's going to be a 10. We still have 10 minutes. So, okay, let me continue this one. Very fast one. So the binary search tree is with the following, that's for every node. We have left and right. So in doing the tree, the searching of the tree, which part that you want to search first? Okay, it's always search to the left, then only you search to the right. But which is the left and right? It's following the roots. So roots is going to be the current nodes. Okay, roots is going to be the current nodes. You go to the left and right. But when it comes to the subtree, of course, here, E will be the current nodes for the subtree. Left, okay, left, here, this part is left and this part is the right. Same for the right side over here. Let's say if we go to the subtree of L, L would be the current nodes. And J, okay, would be the right, left side, and M would be the right side. So if you're trying to search through the tree, you can decide what is the pattern for the searching that you want. But of course, you have to know how you arrange your data in a tree form. So let's say I ask you, I want to find the A in this tree. So how are you going to find it? Of course, you think that, okay, you start to think. H, it will be the middle. Okay, it will be the like current nodes. So where does A place H? Is it left or is it right side? Is right side, right? Because A, B, C, D, E, F, G, then only read H, right? So H is actually, A is actually before the H. So if you arrange your tree properly, means that you know that your A is actually in the left side. So what you do, okay, you're not going to the right side because you definitely know that A is not going to be at the right hand side. It's going to be at the left hand side. So of course, when you come here, you think again, okay, because you expand that you have a subtree E here. So E, where is A to E? Is in the left. So you're not going to check this one. You go to the left and check. But then for B, of course, you know that definitely is actually in the left. So that's how you can actually think of when you try to search through the tree itself. Okay. So why do you need the searching of the tree? Because binary tree itself is very inefficient. Okay. If let's say you have 100 million for the binary trees, then you're trying to find, imagine you're trying to find through every single of nodes. So how can you do it? Of course, this one is, let's say you try to find A, you go through every single nodes over here. It's not a problem because it's just a small tree. But if you have 1 million nodes, how are you going to do it? If you try to find one by one, then it would be slow if you just use a simple operation. So what you're going to do is you have to think properly that how are you going to search through? Because if you find through one by one, okay, it will be n multiply problems. But when you think of like trying to reducing it, it can be a log problem. Can reduce the searching time through the tree over here. Okay, so let's see. So what is the reasons of searching? So this one I already explained that we try to find A here. So definitely you know that it's in the left side. Then you're not going into the right side. So that's why you have the notes of the arrangement with the rules that currents, okay, L and R. So C, which is the current nodes here, is definitely to be larger than the L, and whereas in the right-hand side is definitely greater than the C. So you can see here that how many steps you go. 1, 2, 3. So it's going to go for the how many search? 4 search, where you can actually save the time to be log 2, because only you go to that 14 years is 3.2. So it is actually good. Is a good binary search tree. Okay, I think at this one, I'll continue after we come back from the talk by the special speaker. So we'll stop over here, then we continue. And after when you come back, we go to show you the codes of how the binary search tree can do. And also we go to the graph. All right, I'll see you in 11:30. Okay, bye.